Okay, well, thank you very much for being here. Thanks the organizers for inviting me. It's always a pleasure to be back to UCLA. And so today I'm going to tell you a little story. First, a little bit about me. I'm not a biologist. I come from mathematics and computer science. And so my ambition, to use a big word, is maybe a bit different from most of you, in the sense that my ambition is not to discover new truths and make new claims about living organisms. I wish I could, but I don't feel qualified for this. Rather, it's to explore the possibility of enriching the toolkit of techniques, of mathematical techniques one uses to try to understand complex systems coming from the living world. And I think there's potential for that. There are pros and cons, and I'll get to that. So, no, it's not this one. Yes. So let's start with a simple observation, difference between physics and biology. So if you look how quickly your coffee, your spoon is going to get hot when you have hot coffee, well, math has a good answer. You solve this equation. What's remarkable is that temperature is a rather complex collective observable, because it's sort of average kinetic energy of a quadrillion and quadrillion of particles doing their own thing independently, and somehow take the average of that, and lo and behold, there's an equation that acts on that. Kind of amazing. And it's a super simple equation. It's actually hard to think of anything simpler than that. So what's going on? Are we so lucky? There's something as complex, such a complex system as molecules, particles moving around this thing and getting it hot, has such a simple answer. Okay, I have to learn to press the right button here, sorry. Now, if you ask the same question for tomatoes, why is it red? This is what you've got. Now, you might think, well, it's just because we're stupid. And it should be really something like this, but we're too stupid, and that's what we have. Nobody believes that, okay? I mean, I think that we have to reconcile ourselves that complexity is going to be different in biology. Let's try to understand why. So in mathematics, in physics, is so tied to mathematics because of the presence of symmetries. That the physical universe, for whatever reason, is governed by absolutely astonishing symmetries. Once you have symmetries, then you have invariance in the world of physics, and you can exploit that, and that ends up with this amazing equation that exploits the symmetry to the nth degree. Now, once you have symmetry, you have dimension reduction. Dimension reduction is basically what all of science is about. Science is very complicated. Our brain is very small. We have to make things simpler. We have to reduce this enormous amount of variables to a few we can understand. So that's what these symmetries buy you. You just can sort of drop out lots of variables, and you get differential equations. Anyway, that's in some sense why physics has been so incredibly successful. Now this, what's going on here? Well, I think the first, of course, all of this is physical, so you can say, well, this is just a case of physics, right? But that doesn't get you very far in the story. I mean, the point is that this is evolution that produced this thing right here, and evolution is inherently historical. So this is a really fundamental difference with physics. So this is what I call natural algorithms. Natural means it comes from the natural world, from in particular the living world. And algorithms is really the distinctive feature because algorithms, roughly speaking, is equations, good old equations, plus memory. You see, physics basically does not use memory. And biology is all about memory. Now, for you, memory, for the first part, well, of course, DNA, physics does not have DNA, the solar system does not have DNA. But so that's memory, obviously, but it's much more than that. Now, I speak here as a computer scientist. The miracle of computing is memory. okay? And nothing else. It's not Boolean gates or anything. It's memory. Universality of computing comes from the role of memory. Physics basically does not use memory. And what I mean by this is that when you look at the solar system and try to figure out all these planets, how they go around, you don't need to know almost anything about Jupiter except a point and a momentum. That's pretty much all you need to know, which is totally astonishing. Something as complex as Jupiter can be reduced to basically next to nothing. And furthermore, what happened to the solar system a million years ago is absolutely irrelevant. As long as you have these little numbers, you're golden, okay? This is very Markovian in a very strong sense. The phase space is tiny. It's very, very tiny. And it did not have to be like that. It could have been very complicated, but it's not. And so one gets the impression that biology is going to be very, very different, because this is a story that accumulates, and some of it is irrelevant, some of it is very important, and we are observers, and it's not clear what is what. So my role, again, is certainly not to help come up with a better circuit. I do not have that pretension. I barely understand what those things are. Once we agree this is pretty cool, then what do we do with that? We just simulate it on a supercomputer, or maybe we can reason about it. So that's the sort of thing that I'm interested. Now, I want to make a quick digression, which comes from long discussions with Stein Leibler, a collaborator from Princeton, and Rockefeller. Which kind of struck me. So this is a model of the first steam engine. So this is the Industrial Revolution, late 18th century. So a steam engine is this thing that converts heat, which is mechanical energy, kinetic energy of little particles, into ordered mechanics, force that you can use to do work, and which obviously was very important in industry. I mean, that's how the industrial revolution came about. And so this little gadget received a lot of attention from all the smartest people, mostly in England. This story really started in England, then spread out. So they tried to improve on this. They realized very quickly that a steam engine that they were building had a lot of waste. So ideally, you'd like to convert this heat into mechanical energy and somehow not lose that 100% of what you had in and out. But they tried, and they could see they were losing like half of it, basically. They couldn't. So they built better and better and more complicated. There's a whole industry of simply building steam engines for the Industrial Revolution. And they got more and more complicated. So this is like the big data of the mid-19th century, where these enormously complicated designs for steam engines, which got 0.1% better than predecessors. So you got to buy this one because that's what it is. And some scientists scratch their heads and say, well, I think we're going the wrong way. This is completely crazy. So they started working on this, particular Carnot, Clausius, and Boltzmann, and say, there's only 5 numbers that matter. Everything else is basically a waste of time. Just get these 5 numbers to be on your side, pressure, volume, temperature, entropy, and whatever energy, free energy or enthalpy, whatever that you have. And that's pretty much the full story. Thus was born thermodynamics. But what's remarkable is not thus was born string theory, some kind of incomprehensible science, which only a very few people can understand if they spend 20 years of their lives reading very complicated papers. Thermodynamics is almost, actually, I think it's much more difficult than it seems. But mathematically, it's very simple. It's just fractions, okay? And it's totally, when you think about it, it's totally remarkable, this story. And forget the Industrial Revolution, which is hard to forget. But so the impact was enormous, no doubt. But also just the arc of going more and more complex, more and more convoluted, more and more sophisticated, and then everything collapses. We can teach freshmen, college freshmen. The story, it's all about 5 numbers. That's it. I don't believe biology is going to have these templates. This is too good a story to be repeated. However, I think there's a germ from that story that hopefully can be replicated. That there's some basic principle. Now, pressure and volume are rather trivial things, but temperature already is quite a subtle thing. Entropy is an amazing intellectual concept when you think about it. So is free energy. So these are not just simple things you measure. You really have to think hard before you hit on the right concepts. And so I hope that in biology there will be some kind of arc going this way. This is the end of my digression. And so I cannot design a sort of model organism. The advantage of being purely theoretical is that you can do almost anything you want, because anyway it's irrelevant. So if it's going to be irrelevant, it might as well be fun irrelevant. Whereas people doing actual work with actual animals, which is most of you, I think, you actually are constrained by reality. So I don't have that problem. So the model organism goes like this. You have agents, so these are little red dots, and they are, think of them as endowed with a little computer. You can compute certain things. There's a little computer there, and it has memory. As I say, memory is the key feature. Now, the way the memory is represented is by the dimension. So this graph is embedded in space. So let's say that each one little computer here has 1,000 registers, has 1,000 variables, like pressure, volume, whatever, And let's say they all have 1,000. Then this graph would live in R to the 1,000, okay? It would be embedded, so it's geometry. It would be in this higher space. I draw it in 2 dimensions for obvious reasons, but you can imagine this being very high dimensional. Now, 2 things happen. First, there's a notion of neighborhood, locality. So that's also a very important thing about computing, coming from computer science. The complex system in computer science, a computer is a complex system only driven by local interactions. Okay, it's from local to global. That's one of the key features of computing. So we do the same thing here. And so everybody basically has a bunch of neighbors, and this computer will alter its state by talking to its neighbors, and then figuring out what they have, what information they have, take this information and crank out their little computer that they have, and they come out with new numbers. And so that means that the memory here is going to change. Say, if you have 1,000 registers, they will be updated. But remember, we interpret these registers as the coordinates of a point in higher dimensions. So we are, say, in R1000, which means that this point will move, and this one will move. So this graph will move, the nodes will move, okay, as a result of this interaction. Now, once the nodes are moved, the communication graph is updated automatically, because we assume that the communication graph depends only on the position, on the state of the agents. Now, we can add outside things if you want some kind of a field from outside, or wind, or sure, you can do this. But I would say in its sort of primary form, this is a closed loop system with 2 parts. How do we move the agents, which is a local decision, and how do we update the graph? So the graph is going to change, okay? But I mean, yesterday we heard, almost every talk that we heard yesterday involves some form of that, okay? Like flocking, for example. You can see the agents and okay, so. Now, you know that from a mathematical standpoint, that you're going to have to reason about dynamic networks, that is, networks that change over time. And there will be a dynamical system embedded as a dynamic, so the word dynamic is used twice. And I say, well, that's great. We know a lot about networks. We know a lot about graphs. I mean, for over 100 years, very smart people have really published tons and tons of volumes on graphs. So we're going to use all of this technology and so on. And then you realize that the answer is no, that when you become a dynamic graph, you still inherit the word graph, but basically you inherit almost nothing else. It completely dissolves all this beautiful knowledge about graphs, basically is almost entirely useless. So you've got to invent something else, okay? Why wasn't this invented before? Well, because I don't think people needed dynamic graphs. Why would you need it? you know how hard it is to draw a dynamic graph? Try it when you teach, for example, and you have a graph. You can spend 2 hours talking about search algorithms and chromatic numbers and so on. But let's have a dynamic graph. And if you use a video, as Ian did so beautifully, but it's very hard to say, hey, just follow this guy here. Okay. So now I've confined my attention to what's called diffusive influence systems. So these are influence systems just as I defined. But there's one more technical assumptions, which is that agents move within the convex hull of the neighbors. So this is geometry, right? This is a graph embedded in some space. And we have some metric in there. It's here, we can assume it's Euclidean, but it does not have to be Euclidean, actually. We don't even have to assume it's a metric space right now. And so this guy can only move within the convex hull of these guys. And so that's a restriction. So, but mathematically, this is a very useful property. But how can we justify that? Well, I mean, the reason I justify it is virtually every system I know has this property. Every system we heard yesterday has this property. So, for example, what Orit talked about, that's a diffusive system. The Kuramoto dynamics is a diffusive system. Bird flocking is a diffusive system. Actually, I want to mention, so you saw this movie, so I don't have to, or you saw a different version of the movie, but I don't have to show you. But Ligeti is this Austrian-Hungarian composer who, kind of interesting, creative fellow who had this piece of music, which is 100 metronomes doing the things. And so you see, it's conducive to art. Although it's a bit of an acquired taste to sit through this thing, but it's certainly interesting. So I worked on that as a sort of, again, as a mathematician, really, and just to do the dynamic. I want to understand as a dynamical system, what's going on. So I show that it's very universal in the sense you can have almost any behavior, fixed point period, trying to chaotic. It's Turing complete. So Turing complete means that, well, forget what it means. That's not what's interesting about Turing complete. The implication, there's something called Rice's theorem, which says that if something is Turing complete, every non-trivial question you have about it is undecidable. Every non-trivial question. So you have to define trivial, but trivial is defined trivially. It's kind of like, how many birds do you have? That's a trivial question, so that's decidable. But any, like, there's a door, will they ever go through the door? That's undecidable. In general, doesn't mean that your system is undecidable, okay? But the interesting part of this work was to show that actually, with probability 1, basically, under any perturbation, this is what's going to happen. There's going to be a fixed point attractor, or it's going to be periodic or quasi-periodic. So it's going to be a very simple dynamical mode, almost always. And that got me very intrigued by these. That's also a concern that comes from computer science, but maybe also in biology. How do you engineer slow clocks? So this is a very Turing-like question. How do you get a computer to run as long as possible, but not infinity? It's very easy to have a computer run forever, just have a loop. So I want to write a program that runs as long as possible, but it has to terminate at some point. Now, this is a very hard question. Okay, very hard question. Actually, the answer to this question is undecidable. So more practically, I was really interested in how slow clocks emerge. So for example, when you do Markov chain stuff, you can never get anything more than exponential. Now you might tell me, well, exponential is big enough for me. That's true. But I'm interested in the sort of the theoretical underpinning of this thing. So maybe it's good enough for you, but not for me. I need to understand why exponential. You can never get anything more than exponential. Or 1 over exponential. Say, if you want something very slow, something that happens like a clock, where there's a tick every every exponential number of the size of that machine that you're designing. So I was really interested in that. Now here's a cheating way of having slow clocks, which I'm not interested in, which is when you approach chaos. So when you go from here to here, see this perturbation. So when you tweak with the parameters and you approach chaos, then you have this sort of periodic doubling phenomenon, very, very well-known phenomenon in bifurcation analysis. And so you get systems that are periodic and they double the period and double the period. And so if you just push the knob close enough to criticality, you can get any period you want. But that's cheating because these are totally unstable situations. If you move by epsilon, you lose that. So I want a robust clock. You can shake it and so on, it's still going to work. So this work led to the design of all kinds of really interesting, super, super slow clocks. And we tried to investigate, but I need the help of people like you. So I got interested also in the context of biology because these time-scale ratios in biology are kind of weird. I mean, basically chemical pathways. A chemical reaction can be a millionth of a second, and extremely quick. But we talked about cicadas yesterday. It's like 17 years, 13 years cycle. To go from 10 to the minus 6 seconds to whatever the number is of seconds in these like 15 orders of magnitude. So here you're talking about a very slow clock, that thing. Unless you find some other explanation. Maybe every 17 years, the rings of Saturn do something that the Earth feels, and these insects have to go out. Okay, so that would take care of that. But if we believe that it's more like a circadian thing, which is actually engineered by various protein concentration, blah, 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 then it's a very interesting mystery. Also, the fact that, but I'm digressing, that the cicada periods are always prime numbers. Right? Maybe it's a coincidence. There are many small prime numbers. But still, they're always prime numbers. There are all kinds of explanations for this, but okay.
So could I just pin you down on like what the assertion is over here? So you told us about the diffusive agent-based model.
Yes.
So are you saying that every diffusive agent-based model within this class, where the rules
Yes.
are within
Yeah.
convex, always leads to kind of fixed point or periodic
Yes.
attractor dynamic?
Yeah, exactly.
And that at the same time that this model is Turing complete.
Yeah, because you can tweak it. You can change the parameters. It's like a temperature, and you change the parameters to bring it into a state of criticality. But I have to be perfectly honest, that this talk is a giant scam, swindle, because I really have not defined the model. Like, I would have to define.
That was the question.
No, I haven't defined the model. And so your question makes perfect sense until you realize that I'm basically pulling a fast one on everybody, because I'm not defining anything. So at least you cannot contradict me. That's the advantage. So I'll always be right. But you have to believe that somehow, somewhere in the world, it's defined somewhere, but just not in this room. Okay. And so I'm interested in the tools. So topological entropy, this concept, that's old school, that's old style. Okay, fine. So you can use your typical, dynamics toolkit and use that. And the energy came out of this work. So I want to talk briefly about this. It's a very simple object, mathematical object, which goes like this. So now we assume that we have some kind of metric space. So let's just take Euclidean for simplicity. So this is embedded in R1000, if you want something like that, which means that each edge has a length, a number. And then you have this possibly infinite number of graphs with a fixed number of edges. The edges, we assume that the number does not change. So the S energy is the following. You take this graph, and then you take the length of this edge, and you raise it to the power S. S is a parameter. It's an inverse temperature, actually, but don't have to know that. So you take this length, you raise it to the power S, and you add this guy and this one and this one. So you do the same for all the edges, and you add them up. And then you do the same for the second, the same for the third, blah, 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 blah. You collect all of that, and that gives you a number, E sub S, that's called the S energy. Now, some simple remark is that when you stick S equals 0, then typically this number is 1. So what you end up is summing the number, you're counting the number of edges. So almost surely this number is infinite if you let T go to infinity, which is not very interesting. But I proved something that's not, or at least I don't know any very simple proof, that as long as S is bigger than 0, it's always finite, this number. So you can go, but of course it goes to infinity as S goes to 0. So that's when pushing S to 0 that you're going to have really interesting phenomenon. So this is true only for diffusive system. This is really the key here, that you have to stay in the convex hull. If it's not true, I mean, it's obviously not true in general, because you can just simply concoct things that grow and grow all the time. And so this series is going to be infinite. Now, this is a Dirichlet series. That's what it's called. It can be used as a generating function. And so you can have all kinds of, you can use that, if you can bound that, and so there are techniques for bounding that, then you can use that to estimate the tail of distributions, probability distributions, say, on the edge length and stuff like this, which is very important, of course, in the context, say, of consensus. When you have agents, consensus means that they all come together as one cluster, which means that this thing, each term should go to 0. So I want to talk about 4 different kinds of diffusive influence systems. Some of them you've seen before, and others perhaps not. So this one was mentioned yesterday, I think by Ian. It's a simpler version of flocking. Flocking is more difficult. And again, let me just one more time for these models are not mine. Put a name there. Second, for all I know, they're complete garbage. And third, I don't care. So let's make sure that we're on board, okay? And maybe I'm a madman, but I can justify this on non-mad grounds, that in the process we're going to learn something. For example, S energy. So maybe this model is totally stupid, but at least the S energy now is for good. And that I can justify. It's a really, really interesting idea. Okay, so so what's going on here? In the model, everybody, like you're here and you have political opinions maybe, and so you could be on the right or on the left, you could be authoritarian, you could be libertarian. So you have a position. Your memory, if you will, is your tendency to vote for Trump or to vote for Hitler or to vote for whoever, or me, or and the basis of the model is kind of an interesting tweak, which is you're not influenced by what you listen or hear. You're influenced by what you hear. You have to hear something to be influenced by it, but that's something somewhat similar to you. Okay, so if some crazy madman is shouting, "Let's kill everybody," you can listen to this all day. It's not going to influence you an iota. But if your dearest friends are telling you, I think you're kind of wrong on this, I think you should consider this, then you're going to think hard and say, oh, man, maybe there's a good point, and so you might. So that's the model, the philosophy behind the model, which kind of, I don't know, sounds good to me. And so then you move to the context. So you move. So there's a radius, like bird flocking, there's a radius of influence. So maybe I listen to you and listen to you, I listen to you, listen to you. You guys are too far, I cannot hear you. So I'm going to be influenced by you, and I move my opinions toward the center, the mass center, or something. So if we do this, then we have some magical radius. That's a parameter, we can do whatever we want. And then we do this for everybody. So we get this kind of Voronoi diagram-like things. So you go from 2 dimensions to 1 dimension, and eventually to 0 dimensions. So it converges to something like that. So I show that, I showed with colleagues and students at Princeton, we showed actually this thing actually converges to an attractor, but not asymptotically. It actually at some point stops. and that takes polynomial time. Now in computer science, everything polynomial time is by definition interesting. Maybe we're wrong to be interested, but maybe for you to say, so what? It's I've seen physicists react like this. Maybe they're right. Like there's at some point in the late 90s, there's all these results about the convergence of the Ising model for various spin systems and so on. And computer scientists were very excited, and physicists, I remember I was consulting at NEC at the time, they just said, yeah, we knew that. So they knew that because physicists, they know things, but they don't have to have a proof. But they're right, they're smart people, and so usually they're right. And so they knew that. They didn't know why they knew that, but they just knew that. But they were right because they're smart people. But there was a proof, and they couldn't care less that there was a proof. They say, why do I need to prove something that I know? I mean, think about it. That's interesting. It's a bit arrogant, maybe, but. So the tools here are mostly from combinatorics, okay, which is.
Can I ask a quick question about that last model?
Yeah.
How does it scale with increasing the number of dimensions? Does it become tractable, or can you always, because you just showed 2 dimensions there, right?
Yeah, so here it's polynomial also in the dimension. Yes. Okay. Yeah, and that's a very good question. Yes. So basically it's, so the dimension cannot be bigger than the number of agents because otherwise it can always reduce. But I mean, so it affects the polynomial, yes, obviously, but not as an exponential term. But also, like, if everybody has a different radius, or if they say there are 2 radius, or one radius is 0, and the other is, actually, that we know how to solve. But let's say there are 2 radii, like Ian had in his slide yesterday, there were the alignment radius, and then there was the field radius, the collision radius. Just 2 radii. Nobody knows if it converges. I mean, a physicist would know because it does converge. When you see it on the computer, it converges very quickly, actually. But mathematically, people have tried for 30 years to prove that thing, and they cannot prove it. I wasted a lot of time doing that. So it's so there's this conjecture from these people at MIT that say that when you do this in 1 dimension, so I've reversed the thing. So we're in 1 dimension now, and I put all the agents along this vertical axis. There's so many of them, you cannot see them apart because there's so many of them. In fact, there's an infinite number of them. And so then we run this thing, and then you have this. So it converges to these clusters, and you notice that the spacing is about 2 times r. R is the radius, and which is easy to, if you had to guess, 2r, it makes sense. I mean, it cannot really be smaller than that because then there would be a track. So that's a good conjecture, and it kind of matches empirical evidence. So we couldn't prove that, but we looked at the thermodynamic limit. So when you have an infinite number of agents, and with these collaborators, we actually showed that this number. This is not an algebraic number. It's a certain root of some kind of complicated trigonometric equation. And so it's 2R conjecture, maybe 2.29R conjecture is impossible to remember. So I think 2R is still a good word. But that's what we have. And there it's very similar to what Diffusive said about. So when you go to the thermodynamic limit, then you can use PDEs, like here Fokker-Planck. And for PDEs, there are lots of techniques which we can use to prove this thing. So, I mean, again, I'm interested not so much in the result. I mean, I think it's a good conjecture. It's nice to get a result which is probably correct in the discrete case, even though this is the continuous case. But to me, what's interesting is, number one, to me, it was a bit of a disappointment, even though I think this is very nice work, but because, again, I'm interested in finding new ways of doing things. Just, this is the old way of doing things, and it's almost like a black hole. PDEs are very powerful. We have lots of powerful tools. Now, the discrete continuous, for computer scientists, there's a constant, your brain goes discrete versus continuous, and And you learn that discrete is much more expressive than continuous. Actually, you don't need continuous for anything, pretty much. But in practice, you do, because the tools, when you go to the store for discrete stuff, you have a hammer and a screwdriver, and that's it. When you go to the store for continuous PDEs, you have this enormous arsenal of rockets of all sizes and landmines and just everything, and satellites and atomic bombs, and just everything so powerful that it's not very surprising that we could find a kind of solution in the continuous case, but we still don't know how to prove it in a discrete case. Discrete is too easy. But on the other hand, it kind of fits, what I'm thinking. It's like, if you think this is bad, this gap, well, then go into biology and you'll see. It's going to get even worse than that. Because there's no cancer differential equation. And once we find that cancer differential equation, we'll solve it and we'll cure cancer. It's just not going to work like this. I don't know how it's going to work, but I know it's not going to work like this. Life can be good, but not that good, okay? And so the question again is, what do we do? So going back to the 19th, these are 19th century mathematics. Hopefully is not the thing. Now, bird flocking, that's different. I want to show you this movie, which I stole from YouTube, and which is there. Maybe you've seen it before. And so this is birds flying around. It's kind of pretty. I think this is LA. And anyway, it's a bunch of birds doing the things, and it's kind of pretty. And then there's another one here, the little triangle thing. Nice little birds having a good time. Very nice cinematography. The reason I'm showing it here is because this is all fake. All three are AI generated. And to some extent, they pass the Turing test for humans. I mean, I don't know, you could fool me with this thing, but maybe I'm not a bird expert. But you should ask a bird. So Ian, this has to be your next project. I want birds to be asked to judge the Turing test.
We have a paper in science robotics where we do the Turing test for fish.
No, you're kidding.
That's reality. I can send it to you later.
Oh.
Yeah. So we do exactly that.
Right. I mean, who am I to decide whether you fly like a bird? I mean, come on, this is ridiculous. But yeah, so I need a bird's advice. Yeah. And if I see that they're laughing, then I'll have my answer. Okay. And so thank you. Yeah, I'm really interested. So now this movie came from, had nothing to do with what you guys are doing. It came from the world of virtual reality, and people want to make movies. It came from Hollywood, really. And so there's this guy, Reynolds, who in 1986 came up with these rules. And you'll see these rules are very, in some sense, they're rewording of, there are many models, as Ian told us, and they all kind of a similar flavor, And so anyway, you have those things. So then, I look at this and say, okay, I want to analyze this, and I quickly realized that I'm absolutely incapable of doing that. It's way too complicated. So then there's these shacks that Ian talked about, and then Cooker and Smell worked on this and added some little tweaks. So now there's this model, which again I knew was totally unrealistic, but since yesterday's talk from Ian, then I know it's even doubly unrealistic. But again, I don't really care because it's a good model, and I'm going to learn something about collective behavior, even though there's yet no animals that follow my rules. But when I'm dictator of the animal world, I will train birds to follow not Ian's rules, but my rules. And so the model, now I'm so lame. Like today you see this presentation, they're so gorgeous. When I did this, I thought I did a pretty good job. It's actually pretty shitty, but never mind. Anyway, there's radius and there's birds saying, hey, these are my neighbors, you're flying here, you're flying here, you're flying here. I'm going to average my direction and blah, blah, blah. You've seen this before, and they fly. So this is now, So I wanted to show that the graph, so this communication graph reaches a fixed point. That at some point this graph settles into, there's an attractor, and that's it. At some point is the graph forever, and which is different from alignment. In fact, I'll show you why. This is a much stronger condition. Okay, you can have perfectly aligned things, and the graph constantly changes. And so I thought, and this is an encouragement for the younger people here. Well, it seems everybody is younger, but the young people here, 10 minutes, I got to hurry up, I forget what the young people here are doing. Yeah, I thought this would be really simple. Those questions usually are not that hard. They should not be hard. And I spent more than 2 years. I have a 100-page paper. It turned on into a nightmare. But yeah, for the younger people, the moral of the story is overestimate your intelligence. This is a good thing. No, you really have to, because my attitude was, oh, come on, I know how to do that. I was being totally dumb because that was not true, it turns out. But imagine if I had gone the other route. Oh my God, this is way too hard for me, and then I would have moved on. So you don't have to inflict this on others. It's just to yourself when you speak to yourself in the mirror, and you go, I think I can do that. Yeah, fool yourself. I recommend that to a point. And then with the student, we showed that the number is bounded, the number of flux is the number of kinetic components. Okay, so here's what happened, that those guys fly kind of random and they fragment and so on. And then at some point they will merge into flux. And this is a time at which they can never get separated now. But the graph, so once they reach that phase, there cannot be any fragmentation anymore. Whoever has merged, if you and I belong to the same flock, now we'll stay in the same flock together. However, the time to merge can be unbelievably long because they can be almost perfectly aligned, and they get more and more aligned. So you don't know whether they'll ever merge or not. And so to prove that actually there's a bound after which is decided is not the easiest thing in the world. I'm still doing that. Okay, so I want to skip this. Oh yeah, now something I want to say is that there is, this paper is full of geometry. In mathematics, I come from geometry. This is my field. And so I was very happy with birds because I thought this is going to be lots of geometry. And that's reading all these papers, and it's remarkable. You would never know that they fly from reading the papers. It's all statistical mechanics and so on. You would think they're steam engines or they're magnets. But no, but they fly, in 3 dimensions. There's lots of possibilities. So this has a lot of geometry, so that was pretty cool. A flock is a damped oscillator, a couple oscillator. And the interesting thing is, so when they fly on their own, if you look at the power spectrum, then there's the speed that's constant. And then there's those guys that get smaller and smaller, because as you iterate, these eigenvalues are less than 1 and they sort of go to 0. But the interesting thing is when they collide, when two things get together, then the spectrum, this is really interesting. So what happens is that there's the spectral shift, that this energy over here somehow gets combined and moved over to determine the velocity here. It moves over here. So I asked the physicists at Princeton if they've ever seen like this, and they sent me to a paper in quantum mechanics, which I could barely understand. But some might say, yeah, it's the same phenomenon. Okay, but don't ask me questions about why. And so, okay, so something else I want to spend a little time that I have. I have 5 minutes left?
Yeah, you have about 7 minutes.
7 minutes, okay. Which I think is, renormalization. So this is the concept that was addressed yesterday by Denai and others about reading things at different scales. So, at some point when you look at this, you want to say, this behavior is very much like the superbird. And so it'd be kind of nice to be able to infer local rules from the birds to new local rules for superbirds, which in statistical mechanics you do all the time. I think Ian mentioned Wilson's work on renormalization, and so I'm going to skip this if you don't mind, and I want to talk about this, and this will be a nice way of concluding. So the field where I come from, there are hundreds, thousands of works in the literature where we take a graph and we try to cluster it. Take a graph and you cluster it into what makes sense. And then maybe you do hierarchical clustering. You cluster the clusters, then cluster the clusters of clusters. And you try to do it in a way that makes sense. And typically what happens is you define some kind of metric, some kind of geometry, and then you optimize some cost function. And there are many ways of doing that. But notice, it's a purely syntactical approach. It never asks the questions, why are you doing this? It's a bit like information theory, right? I mean, the success of information theory, it was totally devoid of semantics. They never ask you, what are you trying to say through this channel? No, we don't care. Show me your bits, and I'll make sure they're secure. And same is true in clustering. And I thought, I'm a big soccer fan, being European, and from the age I was a kid, I did hierarchical clustering in my head. Had nothing to do with Euclidean clustering, but I knew on the soccer thing who was clustered with whom and why. And they're not doing it because they happened to be close by accident. No, their job was to mark this. The job was to pass over here. The job was to create space. The job was to counter somebody else opening space. There's all these strategies, and the clustering of the graph tries to reflect these kind of things. So I really was dying to get some students to work on this thing, but living in the US, I couldn't find anybody who knew anything about soccer. But I found somebody who knew a lot about basketball, and furthermore had access to this treasure trove, this huge database. For some reason, virtually every NBA game is available in forms of video in some kind of archive, which is publicly available. And I hope it's publicly available because my student told me so. I hope he didn't hack into some kind of thing. So we had this project, which was really, we published something, but it's really work in progress. It's not. But I like the motivation. So the motivation is this. So you're a Martian and you land on planet Earth, and then you see these basketball games. You don't even know what the rules are. You've never seen a basketball game, and you're given these trajectories. So first, we produce this passing network. And then I'll go through this in the 30 seconds that I have left. But the goal is this. Is it possible to go from syntax to semantics? In other words, I'm going to be looking, I know you're playing a game, I know there are two teams, and that's it. And then I just see what you're doing, and my goal is to infer the rules of the game, and then the strategies. What would a coach do? What would a point guard do? What would a center do? What a blah, 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 blah. To understand the semantics of the game being played from the data. And therefore, this sort of relation from syntax to semantics, to me, resonates a lot with what people are trying to do in deep learning, but also in the field of applied science, of biology and ecology and things, economics and things like this. So this was kind of interesting. I'm pretty sure I've run out of time. Oh, I have 2 minutes. I can sing a song if you want. So anyway, so I could spend more time on this. So this is a library, but basically we have this alphabet of basic graphs that represents motifs, if you will, of passing. And then we have a grammar over this, and we can build a parsing tree where, given a video of a game, we can parse it as you would parse a sentence in some formal language, and so on. And so what I want to conclude with is the kind of curse of mid-dimensionality. The field of dynamics was invented in order to deal with the solar system. And solar system does not have too many planets. It's chaotic. We know that, and Poincaré learned the hard way that it was chaotic. But there's all this theory, CAM perturbation theories. There's all this sophisticated theory that says that even though it's chaotic, it's not chaotic for the next 200 million years. And meanwhile, we can still give amazingly accurate predictions. So we can treat it as a low-dimensional system, basically, that has good behavior. So it's a big success stories. Now, curse of dimensionality is that when you have too many things, it's too complicated. It grows exponentially, the complexity. So then you're very limited. Except that it's not quite true. When it's extremely high, say in physics, in thermodynamics, but the number is Avogadro's number, it's a gigantic number. And if you take the exponential of that, forget about it. And yet we can do thermodynamics, we can do all statistical mechanics, we can do all sorts of things very efficiently. Well, again, it's because of the symmetries I was talking about earlier, everything cancels basically. I mean, the way of looking at these collectives is that they're basically neutralized. And as a result, there's a very simple, slow motion that comes out of these agents struggling for attention, but to some extent, the local thing is irrelevant. They all average out to some coherent behavior. And so this is, again, a lucky, I don't think there's a philosophical argument why it has to be like that, but it is like that, so we should enjoy. But really what's difficult is biology, is what you guys are doing, because there are not enough birds and too many birds, okay? And so you can treat this as a gas, and maybe it's going to work in some things, but at the end of the day, you cannot just say that anything birds do is just like a gas coming out of a pump. This is not going to work. So this is really how we deal with this thing, need new math. Okay, and then I will stop. Thank you very much for your attention.